First, I would like to thank all the organizer for inviting me. I'm 60% statistician, 30% mathematician, and 10% ecologist. So, so I actually know little about genetics, but I think interaction between different disciplines, advanced science. Please bear with my non-native English. Also bear with my mathematical equations. I would like to remark that now it's midnight in my country, so I actually in sleepy mode. So if I say something that you don't understand, that must be Chinese. So first, I would like to cite Nanny. Nanny said that we are all blind men and women trying to describe a monstrous elephant of ecological and evolutionary diversity. So there are so many diversity measures, different measures quantify different aspects. So my apology if my aspects are different from yours, and my indicators here are different from yours. I would like to offer two ecological perspectives that might be useful in analyzing genetic data. First is I would like to offer that instead of using a few indices, use a curve I could Hill numbers profile to quantify species diversity or phylogenetic diversity. The second point that might be useful is that standardization method. Instead of standardizing sample sizes, we standardize sample completeness based on the concept of sample coverage. This was developed by Alan Turing, who is regarded as the founder of modern computer science. So I think there are three dimensions in ecological diversity: species diversity, phylogenetic diversity, also functional diversity. I use a small sample data set to show you how the ecological data set look like. This data set contains a total 43 plant species and collected in 3 habitats along the coast in Italy. The 3 habitats is embryo, mobile, and transition dunes. So there are the species diversity. We just consider species richness and abundance involved in each habitat. So here is the relative is the abundances. It's just a number of individuals for each species in each habitat. And for the phylogenetic diversity, we also consider the evolutionary history between this observed species. And for the functional diversity, that is, we consider the functional distance between species. For example, each species was described by 16 plant functional traits. So these are the functional traits for this for the 43 species, and we use the functional distance between species to quantify ecosystem diversity or functional diversity. So back to the indices, the most widely used heterozygosity corresponds to Gini-Simpson index in ecology. And this index means that we take 2 individuals, the probability that they belong to different species, which is expressed as in this mathematical formula. And the high probability means high diversity, and one complement of this index is called Simpson concentration or repeat rate. So repeat rate is high, means diversity is low, and all these mathematical formulas is in terms of species relative abundances. Another widely used indices is Shannon's entropy. that is the uncertainty. It quantifies the uncertainty in the species identity of a randomly sampled individual, and Shannon's entropy can be expressed as in this form. The Gini-Simpson index or Shannon entropy both are widely used in many disciplines. However, an essential minimum requirement for diversity that ecologists expect is the doubling property from MacArthur. That means, suppose there are two completely distinct, no overlap species community, each with diversity X. If we combine these two such equally large communities, the diversity should be doubled. This doubling property is called the replication principle in economics. So I use a simple example here to show you that, for example, here we have 4 species and another set of 4 species. When we combine these two communities into this community, of course, species richness satisfies this doubling property because 4 plus 4 is 8. However, entropy does not satisfy because here entropy is log 4 and here is another log 4, and the sum of 2 log 4 is not, of course, is not log 8. Also, heterozygosity does not satisfy the doubling property. And MacArthur found that entropy is in unit of information, but if we take exponential of entropy, it behaves just like species richness. Also, Gini-Simpson is a probability, but if we take inverse of Simpson concentration, it behaves just like species richness. So all these indices have the same unit of species. Of course, the community you have encountered is not simple like this one. However, if a measure cannot satisfy replication principle, in this simple case, we would not expect it work for complicated cases. So this is just basic test for whether a measure can be quantified, can be used as a diversity measure. And Hale integrate the three measures into a family. Now we call Hale numbers, which can be expressed as in this formula. In terms of those relative species relative abundances, also important here is the diversity order Q, and Q equals to 0, 1, 2, reduced to the 3 measures I just mentioned. So what's the basic idea for this Hale's number? You can consider here, this is our observed community. It's complicated because PI may be different. Some are abundant and some are rare. But we can map this to a simple reference community, which is equally common with these species. So here we take the pi to the power q and the sum over I, and we just do the same. We just do the same thing for this reference community, and we let these two functions equal. Then we get this d. D is just Hale's numbers. So what's the interpretation of the order Q? This order Q determines the measure's sensitivity to species frequencies. For example, Q is greater than 1. That means we put more weight on common species. So diversity of order 2 is interpreted as the effective number of dominant species. And for Q equals less than 1, is we put more weight on rare species. So for D of diversity 0 is just species richness. The most important measure is actually Q equals to 1. This weighs species by their frequencies without favoring either common or rare species. So O for any order Q, excuse me. So for all OQ, Hill's number is just in the same unit of species. So we can plot Hill's numbers as a continuous function for order Q. So the plot look like this. That is, we quantify species diversity using a curve rather than just a few numbers. For equally common community, we have a horizontal. We plot here is a Hill's number with respect to Q. For equally common community, we have a horizontal line, and the slope of each profile quantifies the degree of evenness. So we have a slightly uneven, it decreases slowly, and if it's highly uneven, it will decrease sharply. So now we back the example, the 3 habitat, and we just use a curve, the profile, to quantify species diversity of each habitat. And instead of just use species richness, exponential Shannon entropy, and inverse of Simpson, we use a curve to quantify species diversity. And from this curve, you can compare community easily. And now back to the phylogenetic diversity. As Dan said, if we count, Dan's called this a feature. We count each unit of branch length as a species. Then we can easily extend the Hill's number to this phylogenetic diversity of order Q, which can be expressed as in this elegant formula. And this formula is in terms tree depths, also number of branches, also the length of branches, and also the total relative abundance. It's node abundance, it's total relative abundance descended from branch I. I just like to remark that when Q equals, this is also a class of measures in terms of diversity order Q. If order Q is 0, it's just reduce the famous phase PD, it's total branch length. But in this class, we can also incorporate species abundances for equals to 1. It's a transformation of phylogenetic entropy. For Q equals to 2, it's in terms of quadratic entropy, which is the basic measure of AMOVA, that's the analysis of molecular variance. So we have just seen the species diversity. Now we can see the phylogenetic diversity. We also use curves in terms of a few, instead of using a few indices. So it's very elegant. We quantify species diversity using this Hill's number profile. And we quantify phylogenetic diversity use these 3 lines. You can see the ordering are consistent, but the magnitude of the relative difference between 2 habitats are different. Here, the shaded area is a 95% confidence interval to reflect uncertainty of your sampling data. But for this data set, I use this data set because this data, we have observed all species in this small data set. However, in ecology, some sampling data are incomplete. That means there are undetected diversity in samples. So we need a standardization method because observed diversity increase and strongly depends on sample size and sample completeness, especially people using different scale, so that you cannot compare directly the empirical diversity. We need some standardization method. The conventional method for standardization is just use it's a standardized sample size. For this standardized sample size, which can be smaller than the observed sample size, this is the classical rarefaction. And now we can do the extrapolation. However, For this standardization sample size of sampling effort, what are the limitations? A given sample size may be sufficient to find all species in one community. It may find just a small percentage of species in another highly diverse community. Therefore, if we standardize by sample size, this means they may just represent different degrees of completeness. So this sample size is just determined by investigators rather than some characteristics of community. So Lou is there. Lou and I propose using standardization by sample completeness. That is, we compare equally complete samples rather than equally sized samples. But the problem, the basic problem, is how we quantify sample completeness. We borrow wisdom of Alan Turing. Alan Turing, in his code-breaking work, developed a concept called sample coverage. That is the fraction of the individuals in an assemblage. This assemblage includes all the undetected individuals that belong to species observed in a sample. This is a very objective measure of sample completeness. And Turing showed that this sample coverage can be very accurately estimated based on the sample itself. And this standardization compared with sample size standardization is superior, both in terms of judging the magnitude of difference in diversity, and also is superior in ranking assemblage efficiently. So I use a two large data set to show you how we do this kind of standardization. These are two rainforests in Brazil. It's one habitat is the age. It's along age forest, and also interior. That about 300 meters from the nearest age. And you can see the age habitat and interior habitat. There are so many observed species, over 300, and their estimate sample coverage about 94%. But notice in both habitats there are a lot of singletons. This in mathematics means there are a lot of undetected species. So here I show you how we do the rarefaction and extrapolation for species richness. And for the data set, we just have two dots. The two dots here means the observed sample. We can do the classical rarefaction, it's the solid line here, and also the extrapolation. This is based on sample size standardization. And we have the shaded area, means 95 confidence interval. So from this curve, we can easily compare these two habitats. And this, the number after arrow sign means asymptotic estimate of species richness. In statistics, we can infer how many species that were not detected in the sampling data. So this is the traditional standardization based on number of standardizing number of individuals or sample size. So this is what we proposed. We proposed compare two habitats based on sample coverage. So you can see the ordering are still the same, but here is that we based on a fraction of individuals rather than sample sizes. And one good thing here is that the confidence interval here overlap. That means data do not provide sufficient evidence to show the statistical significance. However, for this sample coverage standardization, the two confidence intervals are not overlapped. So that means the data are sufficient to detect statistical significance. So this is our standardization for species richness. Similarly, we can do the same rarefaction and extrapolation for phase PD. And here you can see that the two confidence intervals are not overlapped. So we have sufficient data to show this, the statistical difference between the two habitats. So similarly, we can do the same standardization for hills, any member of hill numbers, that is species diversity. And also we can do the same standardization for phylogenetic diversity. So I hope this kind of standardization will be useful for analyzing genetic data, because when we do the statistical consulting, people usually will ask me how we compare diversity for different scale. So this is the solution. We compare diversity for different scale or by using rarefaction and extrapolation for different diversity measures. Also, people usually ask how often we should take a data set. From statistical perspective, the answer is to find the sample completeness. If your sample is almost complete, then you don't need to take more data set. However, if your sample is far from complete, which can be measured by the statistics developed by Alan Turing, then you should take more sampling data. So finally, I would like to remark the additional advantage using this kind of framework. That is, this can be easily extended to attribute diversity. That is, we can assign an attribute value for each species or each node or each species pair. So if the attribute value is branch length, then we get this phylogenetic diversity. If the attribute is the functional distance between species, then we get the ecosystem diversity. But today I just focus on species diversity and phylogenetic diversity. But similarly, we can do the ecosystem or functional diversity. Also, because this measure satisfies doubling property, we can make a meaningful diversity decomposition when there are multiple assemblage over space or over time scale. And that means we can decompose the diversity of the pool assemblage, that's the gamma diversity, into within alpha diversity and beta diversity. And this is work by my collaborator Lou, and maybe Lou can help comment on this aspect. So thank you for your listening.